In this lecture, we develop the weak law of large numbers. Loosely speaking, the weak law of large numbers says that if we have a sequence of independent random variables with the same distribution, then the average of these random variables, which is called the sample mean, approaches the expected value of the distribution. In this sense, it reinforces our interpretation of the expected value as some kind of overall average. The weak law of large numbers is the reason why polling works. By asking many people about the value of some attribute, and by taking the average of the responses, we can get a good estimate of the average over the entire population. On the mathematical side, in order to derive the weak law of large numbers, we will first need to develop some inequalities, namely the Markov and Chebyshev inequalities. Both of them tell us something about tail probabilities. Suppose that A is a number. Then it is reasonable to expect that the probability that the random variable exceeds A will be small when A is very large. But how small? The Markov and Chebyshev inequalities give us some answers to this question based only on knowledge of the mean and the variance of the distribution. Finally, we will have to deal with a technical issue. The weak law of large numbers talks about the convergence of a random variable to a number. For this to make sense, we need to define an appropriate notion of convergence. We will introduce one such notion that goes under the name of convergence in probability, and we will see that in many respects it is similar to the common notion of convergence of numbers. In this segment, we derive and discuss the Markov inequality, a rather simple but quite useful and powerful fact about probability distributions. The basic idea behind the Markov inequality, as well as many other inequalities and bounds in probability theory, is the following. We may be interested in saying something about the probability of an extreme event. By extreme event, we mean that some random variable takes a very large value. If we can calculate that probability exactly, then of course everything is fine. But suppose that we only have a little bit of information about the probability distribution at hand. For example, suppose that we only know the expected value associated with that distribution. Can we say something? Well, here is a statement which is quite intuitive. If you have a non-negative random variable and I tell you that the average or the expected value is rather small, then there should be only a very small probability that the random variable takes a very large value. This is an intuitively plausible statement, and the Markov inequality makes that statement precise. Here's what it says. If we have a random variable that's non-negative and you take any positive number, the probability that the random variable exceeds that particular number is bounded by this ratio. If the expected value of x is very small, then the probability of exceeding that value of a will also be small. Furthermore, if a is very large, the probability of exceeding that very large value drops down because this ratio becomes smaller. So that's what the Markov inequality says. Let us now proceed with the derivation. Let's start with the formula for the expected value of x, and just to keep the argument concrete, let us assume that the random variable is continuous, so that the expected value is given by an integral. The argument would be exactly the same as in the discrete case, but in the discrete case we would be using a sum. Now, since the random variable is non-negative, this integral only ranges from 0 to infinity. Now we're interested, however, in values of x larger than or equal to a, and that tempts us to consider just the integral from a to infinity of the same quantity. How do these two quantities compare to each other? Since we're integrating a non-negative quantity, if we're integrating over a smaller range, the resulting integral will be less than or equal to this integral here. So we get an inequality that goes in this direction. Now let us look at this integral here. Over the range of integration that we're considering, x
is at least as large as a, therefore the quantity that we're integrating from a to infinity is at least as large as a times the density of x. And now we can take this a, which is a constant, pull it outside the integral, and what we are left with is the integral of the density from a to infinity, which is nothing but the probability that the random variable takes a value larger than or equal to a. And now if you compare the two sides of this inequality, that's exactly what the Markov inequality is telling us. Now it is instructive to go through a second derivation of the Markov inequality. This derivation is essentially the same conceptually as the one that we just went through, except that it is more abstract and does not require us to write down any explicit sums or integrals. Here's how it goes. Let us define a new random variable y, which is equal to 0 if the random variable x happens to be less than a, and it is equal to a if x happens to be larger than or equal to a. How is y related to x? If x takes a value less than a, it will still be a non-negative value, so x is going to be at least as large as the value of 0 that y takes. If x is larger than or equal to a, y will be a, so x will again be at least as large. So no matter what, we have the inequality that y is always less than or equal to x. And since this is always the case, this means that the expected value of y will be less than or equal to the expected value of x. But now, what is the expected value of y? Since y is either 0 or a, the expected value is equal to a times the probability of that event, which is a times the probability that x is larger than or equal to a. And by comparing the two sides of this inequality, what we have is exactly the Markov inequality. Let us now go through some simple examples. Suppose that x is exponentially distributed with parameter equal to 1, so that the expected value of x is also going to be equal to 1, and in that case we obtain a bound of 1 over a. To put this result in perspective, note that we're trying to bound a probability. We know that the probability lies between 0 and 1. There is a true value for this probability, and in this particular example, because we have an exponential distribution, this probability is equal to e to the minus a. The Markov inequality gives us a bound. In this instance, the bound takes the form of 1 over a, and the inequality tells us that the true value is somewhere to the left of here. A bound will be considered good or strong or useful if that bound turns out to be quite close to the correct value, so that it also serves as a fairly accurate estimate. Unfortunately, in this example this is not the case, because the true value falls off exponentially with a, whereas the bound that we obtain falls off at the much slower rate of 1 over a. For this reason, one would like to have even better bounds than the Markov inequality, and this is one motivation for the Chebyshev inequality that we will be considering next. But before we move there, let us consider one more example. Suppose that x is a uniform random variable on the interval from -4 to 4. And we are interested in saying something about the probability that x is larger than or equal to 3. So we're interested in this event here. So the value of the density, because we have a range of length 8, the value of the density is 1/8. So we know that this probability has a true value of 1 over 8, which we can indicate on a diagram here. Probabilities are between 0 and 1. We have a true value of 1 over 8. Let us see what the Markov inequality is going to give us. There's one difficulty, that x is not a non-negative random variable, so we cannot apply the Markov inequality right away. However, the event that x is larger than or equal to 3 is smaller than the event that the absolute value of x is larger than or equal to 3. That is, we take this blue event and we also add this green event, and we say that the probability of the blue event is less than or equal to the probability of the blue together with the green event, which is the event that the absolute value of x is larger than or equal to 3. So now we have a random variable which is non-negative, and we can apply the Markov inequality and write that this is less than or equal to the expected value of the absolute value of x divided by 3. What is the expectation of the absolute value of x? X is uniform on this range. The absolute value of x will be taking values only between 0 and 4, and because the original distribution was uniform, the absolute value of x will also be uniform on the range from 0 to 4, and for this reason the expected value is going to be equal to 2, and we get a bound of 2/3. This is a pretty bad bound. It is true, of course, but it is quite far from the true answer. Could we improve this bound? In this particular example, we can. Because of symmetry, we know that the probability of being larger than or equal to 3 is equal to the probability of being less than or equal to -3. Or the probability of this event, which is the blue and the green, is twice the probability of just the blue event. Or to put it differently, this probability here is equal to 1/2 of the probability that the absolute value of x is larger than or equal to 3, and therefore by using the same bound as here, we will obtain an answer of 1/3. So, by being a little more clever and exploiting the symmetry of this distribution around 0, we get a somewhat better bound of 1/3, which is again a true bound. It is more informative than the original bound, but still it is quite far away from the true answer. Mathematically speaking, the Chebyshev inequality is just a simple application of the Markov inequality. However, it contains a somewhat different message. Consider a random variable that has a certain mean and variance. What the Chebyshev inequality says is that if the variance is small, then the random variable is unlikely to fall too far off from the mean. If the variance is small, we have little randomness, and so x cannot be too far from the mean. In more precise terms, we have the following inequality. The probability that the distance from the mean is larger than or equal to a certain number is at most the variance divided by the square of that number. So, if the variance is small, the probability of falling far from the mean is also going to be small. And if the number c is large, so that we're talking about a large distance from the mean, then the probability of this event happening falls off at a rate at least 1 over c squared. By the way, I should add here that c is assumed to be a positive number. If c was negative, then the probability that we're looking at would be equal to 1 anyway, and there isn't any point in trying to obtain a bound for it. To prove the Chebyshev inequality, we will apply the Markov inequality as follows. The probability of interest is the same as the probability that the square of this quantity is larger than or equal to the square of c. But now here we have a non-negative random variable, and we can apply the Markov inequality with x replaced by this random variable and with a replaced by c squared. So this gives us the expected value of the random variable of interest divided by c squared, but we recognize that the numerator is just the variance, and this is the Chebyshev inequality that we claimed. As an application of the Chebyshev inequality, let us look at the probability of this event, that the distance from the mean is at least k standard deviations, where k is some positive number. Using the Chebyshev inequality with C replaced by K times sigma, we obtain sigma squared over C squared, which in our case is K squared times sigma squared, which is 1 over K squared. So what this is saying is that if you take, for example, K equal to 3, the probability that you fall 3 standard deviations away from the mean or more, that probability is going to be less than or equal to 1 over 9. And this is true no matter what kind of distribution you have. Let us now revisit our earlier example where x is an exponential random variable and we're interested in the probability that the random variable takes a value larger than or equal to a. The Markov inequality gave us a bound of 1 over a, and as we recall, the exact answer to this probability was e to the minus a. Let us see what we can get using the Chebyshev inequality. Now, our random variable has a mean of 1. Let us assume that a is bigger than 1, so that we're considering an event that we fall far away from the mean by a distance of at least a minus 1. That is, we write the probability that x is larger than or equal to a as the probability that the distance of x from the mean is larger than or equal to a minus 1. And now, this event is smaller than the event that the absolute value of x minus 1 is larger than a minus 1. This is because if this event is true, then that event will also be true. And now we can apply the Chebyshev inequality. Here we have the distance of x from the mean, so the Chebyshev inequality applied to the random variable x will have up here the variance of x, which is equal to 1, and in the denominator we will have a minus 1 squared. Notice that if a is a large number, this quantity here behaves like 1 over a squared, which falls off much faster than 1 over a. So at least for large a's, the Chebyshev bound is going to give us a smaller bound and therefore more informative than what we obtained from the Markov inequality. In most cases, the Chebyshev inequality is indeed stronger and more informative than the Markov inequality, and one of the reasons is that it exploits more information about the distribution of the random variable x. That is, it uses knowledge not just about the mean of the random variable, but it also uses some information about the variance of the random variable. In this segment, we derive and discuss the weak law of large numbers. It is a rather simple result, but plays a central role within probability theory. The setting is as follows. We start with some probability distribution that has a certain mean and variance, which we assume to be finite. We then draw independent random variables out of this distribution so that these xi's are independent and identically distributed, IID for short. What's going on here is that we are carrying out a long experiment during which all of these random variables are drawn. Once we have drawn n of these random variables, we can calculate the average of the values that have been obtained, and this gives us the so-called sample mean. Notice that the sample mean is a random variable because it is a function of random variables. It should be distinguished from the true mean, mu, which is the expected value of the xi's, which is a number. It is not random. And mu is some kind of average over all the possible outcomes of the random variable xi. The sample mean is the simplest and most natural way for trying to estimate the true mean, and the weak law of large numbers will provide some support to this notion. Let us now look at the properties of the sample mean. Let us calculate its expectation. By the way, this object here involves two different kinds of averaging. The sample mean averages over the values observed during one long experiment, whereas the expectation averages over all possible outcomes of this experiment. The expectation is some kind of theoretical average because we do not get to observe all the possible outcomes of this experiment. But the sample mean is something that we actually calculate on the basis of our observations. In any case, the expected value of the sample mean by linearity, it is the expected value of the numerator divided by the denominator. Using linearity once more, the expected value of a sum is the sum of the expected values, and since each one of those expected values is equal to mu, we obtain n times mu divided by n, which leaves us with mu. So the theoretical average, the expected value of the sample mean, is equal to the true mean. Let us now calculate the variance of the sample mean. The variance of a random variable divided by a number is the variance of that random variable divided by the square of that number. Now, since the xi's are independent, the variance is the sum of the variances, and therefore we obtain n times the variance of each one of them. And after we simplify, this leaves us with sigma squared over n. We're now in a position to apply the Chebyshev inequality. The Chebyshev inequality tells us that the distance of a random variable from its mean being larger than a certain number has a probability that's bounded above by the variance of the random variable of interest divided by the square of the number that we have here. We have already calculated the variance, and so this quantity is sigma squared over n times epsilon squared. And now, if we consider epsilon as a fixed number and let n go to infinity, then what we obtain is a limiting value of 0. So the probability of falling far from the mean diminishes to 0 as we draw more and more samples. That's exactly what the weak law of large number tells us. If we fix any particular epsilon, which is a positive constant, the probability that the sample mean falls away from the true mean by more than epsilon, that probability becomes smaller and smaller and converges to 0 as n goes to infinity. Let us now interpret the weak law of large numbers. As I already hinted, we have to think in terms of one long experiment, and during that experiment we draw several independent random variables drawn from the same distribution. One way of thinking about those random variables is that each one of them is equal to the mean, the true mean, plus some measurement noise, which is a term that has 0 expected value. And all of these noises are independent. So we have a collection of noisy measurements, and then we take those measurements and form the average of them. What the weak law of large numbers tells us is that the sample mean is unlikely to be far off from the true mean. And by far off, we mean at least epsilon distance away. So the sample mean is, in some ways, a good way of estimating the true mean. If n is large enough, then we have high confidence that the sample mean gives us a value that's close to the true mean. As a special case, let us consider a probabilistic model in which we repeat independently many times the same experiment. There's a certain event A associated with that experiment that has a certain probability. And each time that we carry out the experiment, we use an indicator variable to indicate whether the outcome was inside the event or outside the event. So xi is 1 if A occurs, and it is 0 otherwise. The expected value of the xi's, the true mean in this case, is equal to the number p. In this particular example, the sample mean just counts how many times the event A occurred out of the n experiments that we carried out. So it's the frequency with which the event A has occurred. And we call it the empirical frequency of event A. What the weak law of large numbers tells us is that the empirical frequency will be close to the probability of that event. In this sense, it reinforces or justifies the interpretation of probabilities as frequencies. We will now consider a very practical application of the weak law of large numbers and the calculations associated with it. The application has to do with polling. There's a certain referendum that's going to take place. We're close enough to the day of the referendum so that voters have made up their minds, and there's a fraction p of the population that represents the voters that are going to vote yes. But the referendum has not yet taken place, and you want to find out, to predict or estimate what P actually is. What you do is that you go ahead and you select at random a number of people out of the population, and for each person you record their answer, whether they intend to vote yes or whether they intend to vote no. When we say that the people are randomly selected, what we mean is that we choose them uniformly from the population. And since there's a fraction p that will vote yes, this means that this random variable will be 1 with probability p, and therefore the expected value of xi is equal to p. In addition, we assume that we select those people independently. Now, note that if we select people independently, there's always a chance that the first person polled will be the same as the second person polled, something that we do not really want to happen. However, if we assume that the population is very large, or even idealize the situation by assuming that the population is infinite, then this is never going to happen and this will not be a concern. So how do we proceed? We look at the results that we got from the people that we polled, we count how many said yes, divide by n, and this gives us the fraction of yeses in the sample that we have obtained. And this is a pretty reasonable estimate for the unknown fraction p, the fraction of yeses in the overall population. Now, perhaps your boss has asked you to find out the exact value of p. What should your response be? Well, there is no way to calculate p exactly on the basis of a finite and random poll. Therefore, there is going to be some error in our estimation of p. Then perhaps your boss comes back and says, okay, then try to give me an estimate of p which is very accurate. I would like you to come up with an estimate which is correct within 1 percentage point. Can you do this for me? Your answer might be, okay, let me try polling 10,000 people and see if I can guarantee for you such a small error. But after you think about the situation a little more, you realize that there is no way of guaranteeing such a small error with certainty. What if you are unlucky and the people that you poll happen to be not representative of the true population? So you come back to your boss and you say, I cannot guarantee with certainty that the error is going to be small, but perhaps I can guarantee for you that the error that I get is small with high probability. Or alternatively, I'm going to guarantee for you that the probability that we get an error that's bigger than that is very small. So, how small is it going to be? Let's try to derive a bound on this probability of an error larger than 1 percentage point. Using the calculations that we carried out when we derived the weak law of large numbers, we know that this probability of a large error is bounded above by this quantity. What is this quantity? Sigma squared is the variance of the random variable that we are sampling. And since this is Bernoulli, this variance is p times 1 minus p. And then we divide by n, which in our case is 10 to the fourth, times epsilon squared. Epsilon is 10 to the minus 2, so here we have 10 to the minus 4. Okay, but now what is this quantity? This quantity depends on p, and we do not know what p is. However, if you take this expression and plot it as a function of p, what you obtain is a plot of this type, and the maximum happens when p is equal to 1/2, in which case we get a value of 1/4. That is, the variance of the Bernoulli is at most 1/4. And therefore we obtain this bound here, where the denominator terms have disappeared because they're equal to 1. So you tell your boss, if I sample 10,000 people, then the probability of an error more than the 1 percentage point is going to be less than 25%. At which point your boss might reply and say, well, a probability of a large error of 25% is too big. This is unacceptable. I would like you to have a probability of error that's less than 5%. So, suppose now that we want to change this and make it only a 5% error, 5% or less. How are you going to proceed? Well, you have this quantity here, this upper bound, which we know to be less than or equal to 1/4 divided by n times epsilon squared, which is in our case 10 to the minus 4. We would like this quantity to be less than or equal to 5%, which is 5 over 10 to the second power. And after you solve this inequality, you find that this is equivalent to taking n larger than or equal to 10 to the sixth, and then the 5 together with that 4 give us a denominator of 20. And this number is equal to 50,000. So at this point you can go back to your boss and tell them that one way of guaranteeing that the probability of a large error is less than or equal to 5% is to take n equal to 50,000. So 50,000 will suffice to achieve the desired specs. Notice that the desired specs have two parameters. One is the accuracy that you want, and the other is the confidence with which the accuracy is going to be achieved. Now 50,000 is a pretty large number. If you notice the results of polls, the way that they're presented in newspapers, they usually tell you that there's an accuracy of plus or minus 3 percentage points, not 1 percentage point. That helps things a little. It means that you can do with a somewhat smaller sample size. And then there's another effect. Our calculation here was based on this inequality, which is a Chebyshev inequality, but the Chebyshev inequality is not that accurate. It turns out that if we use more accurate estimates of this probability, we will find that actually much smaller values of n will be enough for our purposes. We will now take a step towards abstraction and discuss the issue of convergence of random variables. Let us look at the weak law of large numbers. It tells us that with high probability, the sample mean falls close to the true mean as n goes to infinity. We would like to interpret this statement by saying that the sample mean converges to the true mean. However, before we can make such a statement, we should first define carefully the word converges. And we need a notion of convergence that refers to convergence of random variables. Here's a definition. Suppose that we have a sequence of random variables. that are not necessarily independent. We say that this sequence of random variables converges in probability. That's the particular notion of convergence we're defining. It converges to a certain number if the following is true. No matter what epsilon is, as long as it is a positive number, the probability that the random variable falls far from this number, that is epsilon or further away from that number, that probability converges to zero as n increases. That is, as n increases, there is higher and higher probability that yn will be close to this particular number a. This is the notion of convergence that we have defined, and notice that this notion of convergence corresponds exactly to what is happening in the weak law of large numbers, and so in particular we can describe the weak law of large numbers as saying that mn, the sample mean, converges to mu as n goes to infinity, but in a particular sense, in the sense of convergence in probability. Let us now try to understand a little better what convergence in probability really amounts to, and we will do that by making a comparison with the ordinary notion of convergence of real numbers. When we're dealing with convergence of numbers, we start with a sequence of numbers, and we are interested in the statement that this sequence converges to a certain limit. What does that mean? What we mean is that the elements of the sequence eventually, that is when n is large enough, will get and stay arbitrarily close to this particular number a, which is the limit. In terms of a picture, here is a, the limit, here is n. We take a small band around this number a, and what we require is that the elements of the sequence eventually get within this band around the number a. They might get outside the band, get inside again, but eventually, that is after some time, the elements of the sequence will only stay inside this band. Now, to translate this into a more formal mathematical statement, which is the mathematical definition of the notion of convergence, we have the following. If I give you some epsilon, epsilon could be a very small number. I form a band around a that goes from a minus epsilon to a plus epsilon. What I want is that there exists a certain time, n0. In this picture, n0 would be here, such that for all times after n0, our sequence stays within epsilon from a, that is, our sequence stays inside this band. Now let us move to the case of random variables and see what convergence in probability is talking about. Here, instead of a sequence of numbers, we have a sequence of random variables. And we're interested in the meaning of the convergence of the sequence of random variables to a particular number. In words, what this means is that if I fix a certain epsilon, as in this picture, then the probability that a random variable falls outside this band converges to zero. So the picture would be as follows. We have again our limit. We fix some epsilon, which could be an arbitrarily small number. For any fixed choice of epsilon, we take this band, and for any given n, we look into the probability that a random variable falls inside that band. So if I am to draw the distribution of our random variable, distribution might be something like this. So there is a certain probability that it falls outside this band. But when n becomes large, this probability of falling outside this band becomes very small. So the probability of falling outside the band becomes tiny, so the bulk of the distribution, that is most of the probability, is concentrated inside this band. And this is true no matter how small epsilon is. If I take a much narrower band around A, I still want all the probability to be eventually concentrated inside that band. Of course, it might take longer, it might take a larger value of n, but I want that when n is very large, the bulk of the distribution is again concentrated inside this narrow band. So, in words, convergence in probability means that almost all of the probability mass of the random variable yn, when n is large, that probability mass gets concentrated within a narrow band around the limit of the random variable. We finally point out a few useful properties of convergence in probability that parallel well-known properties of convergence of sequences. Suppose that we have a sequence of random variables that converges in probability to a certain number a and another sequence that converges in probability to some other number b. We do not make any assumptions about independence. We do not assume that the xn's are independent of each other. We do not assume that the sequence of xn's is independent of yn. We then have the following properties. If g is a continuous function, then the function of the random variables converges to the function of the number. So, for example, the sequence of random variables xn squared is going to converge to a squared. Another fact is that the sum of these two random variables converges to the sum of their limits. Both of these properties are analogous to what happens with ordinary convergence of numbers, and they tell us that in some sense convergence in probability is not a very different notion. We will not prove those properties at this point, but they are useful to know. However, there's an important caveat. Xn might converge to a certain number in probability. However, the expected value of xn does not necessarily converge to that same limit. So convergence of random variables does not imply convergence of expectations, and we will be seeing an example where this convergence does not take place. We will now go through two examples of convergence in probability. Our first example is quite trivial. We're dealing with a sequence of random variables yn that are discrete. Most of the probability is concentrated at 0, but there is also a small probability of a large value. Because the bulk of the probability mass is concentrated at 0, it is a good guess that this sequence converges to 0. Do we have indeed convergence in probability to 0? We need to check the definition. So we fix some epsilon, which is a positive number, and we look at the probability of the event that our random variable is epsilon or more away than what we think is the limit of that sequence. We look at that probability, and in this example it is equal to 1 over n, which goes to 0 as n goes to infinity. And this verifies that indeed, in this example, yn converges to 0 as n goes to infinity in probability. Now we make the following observation. If we are to calculate the expected value of this random variable, what we get is the following. We get a value of 0 with this probability, no contribution to the expectation, but we also get a value of n squared with probability 1 over n. And so the expected value is equal to n, which actually goes to infinity as n goes to infinity. So we have a situation where the random variable, the sequence of the random variables converges to 0, but the expectation does not converge to 0. In fact, it goes to infinity. And this example serves to make the point that convergence in probability does not imply convergence of expectations. The reason is that convergence in probability has to do with the bulk of the distribution. It only cares that the tail of the distribution has small probability. On the other hand, the expectation is highly sensitive to the tail of the distribution. It might be that the tail only has a small probability, but if that probability is assigned to a very large value, then the expectation will be strongly affected and can be quite different from the limit of the random variable. Our second example is going to be less trivial and more interesting. Consider random variables that are independent and identically distributed and whose common distribution is uniform on the unit interval so that the PDF takes this form. Are these random variables convergent to something? The answer is no, and the reason is that as I increases, the distribution does not change and it does not get concentrated around a certain number. The distribution remains spread out over the entire unit interval. But let us look now at some related random variables. Let us define yn to be the minimum of the first n of the x's that we get. So if n is equal to 4 and we obtain these 4 values, yn would be equal to this value. Notice that if we draw more values, then the new values might be above the minimum, in which case the minimum does not change, but we might also get a value that's below the minimum, in which case the minimum moves down. The only thing that can happen is that the minimum goes down, it cannot go up, and this gives us this inequality. So the random variables yn tend to go down. How far down? If n is very large, we expect that we will obtain some x's whose value happens to be very close to 0, which means that yn will go down to values that are very close to 0. And this leads us to conjecture that perhaps yn does converge to 0. This is always the first step when dealing with convergence in probability. The first step is to make an educated guess about what the limit might be, and then we want to verify that this is indeed the correct limit. To verify that, what we do is we fix some positive epsilon and we look for the probability that the distance of the random variable yn from the conjectured limit has a magnitude that's larger than or equal to epsilon. And what we need to show is that this quantity converges to 0 as n goes to infinity, no matter what epsilon is. Now, because yn is a non-negative random variable, this is the same as the probability that yn is larger than or equal to epsilon. Now let us distinguish between two cases. If epsilon is bigger than 1, we're asking for the probability that yn is larger than or equal to a certain number epsilon that's out there. But this probability is 0. There's no way that the minimum of these uniforms will take a value that's larger than some epsilon that's larger than 1. So in that case, this quantity is equal to 0 and we are done. But we need to check that this quantity becomes small no matter what epsilon is. So now let us consider taking a small epsilon, that is some number that's less than or equal to 1. For that case, let us continue with the calculation. The minimum is going to be at least epsilon if and only if all of the random variables are at least epsilon. So this is an equivalent way of writing this particular event here. Now, because of independence, this is the product of the probabilities that each one of the random variables is larger than or equal to epsilon. The probability that x1 is larger than or equal to epsilon can be found as follows. If we have here epsilon, the probability of being larger than or equal to epsilon is the probability of this event here. So it's the area of this rectangle. The base of that rectangle is 1 minus epsilon. And so we obtain 1 minus epsilon for this first term. But because the xi's are identically distributed, all the other terms that we multiply are also the same. And so the answer is this expression here. Now, epsilon is a positive number, so 1 minus epsilon is strictly less than 1, and when we take higher powers of a number that's less than 1, we obtain something that converges to 0 as n goes to infinity. And that's what we needed to verify. Since this is the case for any epsilon, we conclude that the random variables yn converge to 0 in the sense that we have defined in probability. Generalizing from this example, when we want to show convergence in probability, the first step is to make a guess as to what is the value that the sequence converges to. In this example, that value was equal to 0. Once we have made that conjecture, then we write down an expression for the probability of being epsilon away from the conjectured limit, and then we calculate that probability either exactly as in this example, or we try to bound it somehow and still show that it goes to 0. The purpose of this segment is to give you a little bit of the bigger picture. We did discuss some inequalities. We did discuss convergence of the sample mean, that's the weak law of large numbers, and we did discuss a particular notion of convergence of random variables, convergence in probability. How far can we take those topics? Let's start with the issue of inequalities. Here one would like to obtain bounds and approximations on tail probabilities that are better than the Markov and Chebyshev inequalities that we have seen. This is indeed possible. For example, there is a so-called Chernoff bound that takes the following form. The Chernoff bound tells us that the probability that the sample mean is away from the true mean by at least a, where a is a positive number, this probability is bounded above by a function that falls exponentially with n, and where the exponent depends on the particular number a that we're considering, but in any case this term in the exponent is a positive quantity. Notice that this is much better, much stronger than what we obtain from the Chebyshev inequality, because in the Chebyshev inequality we only obtain an inequality for this probability that falls off at the rate of 1 over n. So this falls much faster, and so it tells us that this probability is indeed much smaller than what the Chebyshev inequality might predict. However, this inequality requires some additional assumptions on the random variables involved. Another type of approximation on this tail probability can be obtained through the central limit theorem, which will actually be the next topic that we will be studying. Very loosely speaking, the central limit theorem tells us that the random variable m sub n, which is the sample mean, behaves as if it were a normal random variable with the mean and the variance that it should have. We know that this is the mean and the variance of the sample mean, but the central limit theorem tells us that in addition to that, we can also pretend that the sample mean is normal and carry out approximations as if this were a normal random variable. Now, this statement that I'm making here is only a loose statement, is not mathematically completely accurate. We will see later a more accurate statement of the central limit theorem. In a different direction, we can talk about different types of convergence. We did define convergence in probability. But that's not the only notion of convergence that's relevant to random variables. There's an alternative notion, which is convergence with probability 1. Here is what it means. We have a single probabilistic experiment, and within that experiment we have a sequence of random variables and another random variable. And we want to talk about this random variable converging to that random variable. What do we mean by that? We consider a typical outcome of the experiment, that is some omega, look at the values of the random variable yn under that particular omega, and look at that sequence of values, the values of the different random variables under that particular outcome. Under that particular outcome, y also has a certain numerical value, and we're interested into whether this convergence takes place as n goes to infinity. Now, for some outcomes omega, this will happen. For some, it will not happen. We will say that we have convergence with probability 1 if this event has probability equal to 1. That is, there is probability 1, that is essential certainty, that when an outcome of the experiment is obtained, the resulting sequence of values of the random variables yn will converge to the value of the random variable y. Now, this definition is easy to write down, but to actually understand what it really means and the ways it is different from convergence in probability is not so easy. It does take some conceptual effort, and we will not discuss it any further at this point. Let me just say that this is a stronger notion of convergence. If you have convergence with probability 1, you also get convergence in probability. And it turns out that the law of large numbers also holds under this stronger notion of convergence. That is, we have that the sample mean converges to the true mean with probability 1. This is the so-called strong law of large numbers, and because this is a stronger notion of convergence, a more demanding one, that's why this is called the strong law. Incidentally, at this point you might be quite uncertain and confused as to what is really the difference between these two notions of convergence. The definitions do look different, but what is the real difference? This is quite subtle and it does take quite a bit of thinking. It's not supposed to be something that is obvious. So the purpose of this discussion is only to point out this further direction, but without at this point going into it in any depth. Finally, there is another notion of convergence in which we are looking at the distributions of the random variables involved. So we may have a sequence of random variables, each one of them has a certain distribution described by a CDF, and we can ask the question, does this sequence of CDFs converge to a limiting CDF? If that happens, then we say that we have convergence in distribution, and this is more or less the type of convergence that shows up when we deal with the central limit theorem, because this is really a statement about distributions, that the distribution of the sample mean in some sense starts to approach the distribution of a normal random variable.